Assalamu alaikum. My dear viewers, hop, all of you are fine. Ever wondered why heated metal glows or why the sun emits light? You've probably observed these phenomena in your daily life, perhaps when you've watched the embers of a fire flicker and glow or turned on a light bulb. These occurrences, though seemingly simple, are governed by a fascinating principle in the realm of physics. A principle that explains why objects emit radiation when heated. To understand this, we delve into the concept of black-body radiation. Picture an object so black that it absorbs all the light that falls on it. This hypothetical object is what physicists call a black body. No, it's not something out of a science fiction novel. It's a concept used in the study of physics and thermodynamics, particularly in the fields of light and heat radiation. Imagine a surface so dark it doesn't reflect any light. It doesn't allow any light to pass through it either. It simply gobbles up all the light that comes its way. This is the essence of a black body, but here's the kicker. While it absorbs all incident light, it's also constantly emitting light, or more accurately, electromagnetic radiation. This is due to the thermal vibrations happening inside the object. Now let's dive a little deeper. The term radiation often gets a bad rap, thanks to its association with nuclear disasters and superhero origin stories. But in this context, it's not about radioactivity. It's about energy being transmitted. In the case of a black body, the energy is transmitted as light or other forms of electromagnetic radiation, like infrared or ultraviolet. The radiation emitted by a black body is aptly called black-body radiation. And it's not a constant, unchanging thing. The nature of this radiation, its intensity and its frequency distribution, depends on the temperature of the black body. The hotter the black body, the more intensely it radiates energy, and the frequency of the highest intensity radiation shifts towards the blue end of the spectrum as the temperature rises. This might sound a little abstract, and that's because it is. The concept of a black body is a theoretical one. There are no perfect black bodies in the natural world, but this model helps scientists understand how objects absorb and emit energy. So, black-body radiation is essentially the energy radiated by a perfect absorber of light. It's a fascinating phenomenon that lies at the heart of many scientific principles and applications, from the study of stars and planets to the development of energy-efficient technologies. Now, how can we characterize this black-body radiation? Well, it's all rather fascinating. The characteristics of black-body radiation are the key to understanding its behavior. One of the most noteworthy features is that the spectrum of black-body radiation depends solely on the temperature of the body. That's right. The material properties of the body don't figure into it at all. Whether you're dealing with a lump of coal or a diamond, if they're at the same temperature, their black-body radiation will be identical. Now, let's dig a little deeper into this temperature dependency. The energy distribution of black-body radiation over different wavelengths is explained by the concept of spectral radiance. Spectral radiance is the amount of energy emitted per unit area of the body, per unit solid angle, and per unit frequency range. It's a mouthful, I know, but stick with me. At low temperatures, the body emits most of its energy at longer wavelengths. As the temperature increases, the peak of the spectral radiance shifts towards shorter wavelengths. This is why, for example, a piece of metal will first glow red, then yellow, and finally white as it gets hotter. The color changes happen because the peak of the spectral radiance is moving through the visible spectrum. In addition, as the temperature rises, the total amount of energy emitted also increases. But it doesn't just increase, it increases dramatically. To be precise, the total energy emitted is proportional to the fourth power of the absolute temperature. This is known as Stefan's law, and it's a cornerstone of radiation physics. The temperature dependency of black-body radiation, the shifting of spectral radiance, and the dramatic increase in energy with temperature. These are the defining characteristics of black-body radiation. They're fundamental to our understanding of how objects emit energy. And they're at the heart of fields as diverse as astrophysics and climate science. These characteristics provide the foundation for understanding the behavior of black-body radiation. Let's move on to the laws that govern black-body radiation. The two fundamental laws that rule this realm of physics are Planck's law and the Stefan-Boltzmann law. Both of these laws are pillars of quantum physics and thermal radiation, and they help us understand the intriguing concept of black body radiation. First, let's talk about Planck's law. Named after the German physicist Max Planck, this law describes the spectrum of black body radiation. Imagine the black body as an orchestra, with each wavelength of light as a different instrument. Planck's law is like the sheet music, dictating how each instrument or wavelength should play at any given temperature. It tells us that the intensity of radiation emitted by a black body varies with the frequency of radiation and the temperature of the body. Higher the frequency, lower the intensity, and vice versa. Similarly, at a higher temperature, the peak of the radiation curve shifts towards higher frequencies. It's a beautiful symphony of light and heat orchestrated by the laws of physics. Next, we have the Stefan-Boltzmann law. It's named after two physicists, Joseph Stefan and Ludwig Boltzmann, who independently derived it. This law states that the total energy radiated by a black body per unit area is directly proportional to the fourth power of its absolute temperature. In simpler terms, if you double the temperature of a black body, you don't just double the energy it radiates. You increase it 16-fold. Quadruple the temperature, and the energy radiated surges by a whopping 256 times. It's a dramatic escalation, showing us just how powerfully temperature affects radiation. Together, Planck's law and the Stefan-Boltzmann law give us a comprehensive view of black body radiation. They help us understand how black bodies absorb and emit energy, and how changing temperatures can dramatically alter the radiation profile of a black body. These laws are not just theoretical constructs. They have practical implications in various fields, from designing solar panels to understanding the life cycle of stars. These laws help us predict and understand the behavior of black bodies and their radiation. They are the keys that unlock the mysteries of black body radiation, allowing us to delve deeper into the fascinating world of physics. The concept of black body radiation is not just theoretical, it has practical applications too. Let's delve into some of the main applications of black body radiation, starting with thermal imaging. Infrared cameras, a common tool in thermal imaging, rely on black body radiation to function. They capture the infrared radiation emitted by objects, which is directly tied to their temperature. This allows us to see heat and has proven invaluable in a variety of fields, from firefighting and law enforcement to building inspections and even medical diagnostics. Moving to the larger scale, black body radiation plays a critical role in climate modeling. By understanding how the Earth absorbs and re-emits solar radiation, we can predict changes in our climate. This knowledge helps us track global warming trends and devise strategies to mitigate its effects. In the realm of remote sensing, black body radiation is key. Scientists use satellites to measure the Earth's radiation from space, which tells us a lot about our planet's health. It helps us monitor vegetation, water bodies, and even atmospheric pollution. But the significance of black body radiation doesn't stop at practical applications. It's also fundamental to our understanding of the universe. The theory of black body radiation was a cornerstone in the development of quantum mechanics. It was the black body radiation problem that led Max Planck to propose that energy is quantized, a revolutionary idea that birthed the quantum world. And let's not forget the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation, omnipresent throughout the universe, behaves exactly like a perfect black body. Studying it has provided us with a wealth of information about the origins and evolution of our universe. So, the next time you see a heated metal glow or the sun shining, remember, it's all about black body radiation. You're not just looking at a physical phenomenon, but a principle that underpins our understanding of the world, from the tiny atoms that make up matter to the vast expanses of the cosmos. Hope you subscribe this channel at the end.